A very warm welcome and a very good morning to all of you. I'm Dft Singha and I'll be your host for the day. We are here on behalf of the Y2NPro team to welcome all the enthusiastic guests for an exciting project. So, Young to Niche Professionals, Y2NPro, is a new initiative of IEEE Young Professionals Sri Lanka. We'll be focusing on providing the required experience to the niche communities in different industrial fields and enhancing their knowledge in the respective areas. We need to inform you all that we have shared our event virtual background and agenda via a Google Calendar invitation. So you can set up a virtual background to your video as we are going to have a group picture at the end of the program. So please be prepared to take a photo. The Y2NPro program enables a platform for young industrial learners to enhance their knowledge and get more experience specializing in particular niche technologies by learning from experts in the industry. This program is designed for a small group of people who are actively cooperating in the same professional field or are interested in doing so. As you all know, our upcoming project is a workshop series and a competition. Today, we are going to commence our workshop series on phasor measurement unit titled PMU Design and Applications. So, as the first workshop, today's content will be on fundamentals of PMU. We have already conducted an awareness session to educate you about the workshop series, course content, our speakers, and about the PMU design competition. I must mention that this workshop series and the competition are organized by IEEE Y2NPro in collaboration with the IEEE Power and Energy Society Sri Lanka chapter and IEEEPSL Young Professional Global. Without further ado, I would like to invite Mr. Samitha Wijayasundara, the publicity team lead of Y2NPro, to welcome the gathering. Mr. Samitha is currently working as a software engineer at Zebra Technologies, and he has completed his Bachelor of Science in Electrical and Electronic Engineering at Sri Lanka Institute of Information Technology. Mr. Samitha is the Vice Chair of Collaborative Activities Subcommittee in SLSAC 2022 and the Publicity Team Lead at Y2NPro. He is the former Chairperson of Student Branch of SLEET 2022. Mr. Samitha, over to you.
Thank you, Devani. Good morning, ladies and gentlemen. The Young to Niche Professionals initiative is always aimed to uplift the experience and knowledge of niche communities in various industries. Today, on behalf of the Y2NPro Organizing Committee and IEEE Power and Energy Society Sri Lanka chapter, I would like to welcome you all to the first workshop of the PMU Design Workshop Series and Competition. You will be able to broaden your knowledge on the fundamentals of synchronized phasor measurements today. I am honored to welcome Professor Athula D. Rajapakse, Professor at University of Manitoba and the lead at Intelligent Power Grid Laboratory as our guest speaker for this session. I would like to take this opportunity to welcome all the representatives from IEEEPSL Young Professionals, IEEEPSL Sri Lanka chapter, and IEEE Young Professionals Sri Lanka. Also, I would like to welcome all the participants for your enthusiasm in this workshop series and hope that you will take the maximum out of this session. Thank you. Over to you.
Thank you very much, Mr. Samitha. So, without taking much time to continue the session, we would like to introduce and invite our guest speaker, Professor Athula D. Rajapakse, to share his expertise on fundamentals of PMU with our audience. Professor Athula D. Rajapakse joined the University of Manitoba as an assistant professor in the Department of Electrical and Computer Engineering and currently holds the rank of professor. He has diversified background in power and energy systems related areas. He has completed his Bachelor of Science in Electrical Engineering at University of Manitoba and his Master of Engineering in Energy Technology at the Asian Institute of Technology, Bangkok, Thailand. He has obtained his PhD in Quantum Engineering and System Science from the University of Tokyo. His current research activities mainly focus on power system protection and renewable energy integration. Professor Rajapakse is a senior member of IEEE, a registered professional engineer in the province of Manitoba, Canada, and a fellow of Engineers Canada. He is an active member of a number of SIGWE and IEEE working groups. Please welcome Professor Athula D. Rajapakse. Professor, the spotlight is yours.
Okay, thank you, David, for the kind introduction. And nice to see a large group. I think it is, okay, now I see more than 66 people participating in the Zoom session. Yeah, first, before I start my talk, maybe I would like to thank IEEE Young Professionals Sri Lanka chapter for organizing this workshop series and competition. So as I understand, so this workshop series so aim to impart the knowledge on synchropacer measurements and the PMU design so that you can participate in the competition, right? So this is the first lecture in this series. And so I plan to give you some introduction to this synchronized space measurement. So before I start, maybe I would just explain where I come from. So currently I'm working at the University of Manitoba. So University of Manitoba is like one of the 15 main research universities in Canada. And in the province of Manitoba, it is the main research university. So we have about, maybe slightly about 30,000 students, and out of which about 4,000 are graduate students. In our university, we have a very strong research group in the area of power and energy systems. And we work very closely with the industry, especially with the power system simulation industry. Maybe some of you have heard, and there's a power system simulation software called PSCAD, which has been very widely used in the industry, manufacturers, utilities, and everywhere. So that is basically developed in Winnipeg, where our university is located. And in fact, the original program was developed at the university by a professor. And then we also have a real-time digital simulator, what they call RTDS. So that is basically you perform simulations at the real time. So you need a very powerful computers for doing that. So it's a one manufacturer. The brand name is also RTDS, and that is also located actually in the University Research Park. So technologies, again, developed by our university. So we are working very close with these companies. And also we have protection steel manufacturer and power utility closely working with us. So I am basically affiliated to, I am heading the Intelligent Power Grid Lab. And so the focus of this lab is power system protection and automation. You're also dealing with wide area monitoring and control. So that is this today's topic is coming under that area. And of course, we are studying renewable energy integration into both transmission and distribution grids. So that is a little bit about my background. So in today's talk, I'd like to give a little bit of introduction just to explain why synchropacers are important. And then I will introduce formal definition of synchropacers and some features of the synchropacers. So after that, I will maybe give a very brief introduction to how these synchropacer measurements are used in a wide area monitoring, protection, and control. But I'm not going to discuss more on the application because that's probably going to be the topic of another talk that you will listen maybe in the next week. But at the end, maybe I will maybe a little bit touch on the pace estimation algorithms because I think so. Some of you may be participating in the competition where you had to probably build a PMU, so you probably had to deal with this pace estimation algorithms at one point. So I just plan to give some brief introduction. And if you have any questions, maybe if it's a really important question, you can ask during the presentation, or maybe you can send it to the text as a text message, then I can have a look. Yeah. Any questions? How much time do I have for my talk?
You have 1.5 hours.
So 1.5 hours. Hope I can finish the material within that time. Okay. So if we just looking at the evolving nature of the electricity grids. In the traditional grids, so the power generation is at centralized generating stations, and typically the power flows from central power stations to the load centers. And normally when the load changes, the generation changes to follow the load. And so this kind of power systems are operated based on the historical experience. We know how the system behaves in the past, and then based on that, we can expect how it would behave maybe today, tomorrow, and so on in the next hour. And based on that, we do the controls. And but still, we would like to monitor the whole power system so that we have a good understanding to make the decisions, for example, to start a new generating unit or shut down a generator unit, maybe reroute the power flow by switching some transmission lines and so on. But now this situation is changing because of many challenges that we have. So obviously there's a demand for electricity is increasing, but at the same time there's a counter requirement. We had to reduce the emissions related to electricity, and so to achieve that, we need to integrate more and more renewable energy, right? And of course, that will come with some issues, especially when you're trying to integrate solar and wind energy. And the end of the problem is like many of the equipment that is in the power grid are getting older, so you need to optimally use whatever the available assets. And of course, we need to improve the efficiency of the generation, transmission, and distribution, and so on. And at the same time, we want the power supply to be reliable, and also the resilience is also now becoming very important because the frequency of extreme weather events like hurricanes, tornadoes, floods, and everything is becoming more often or more frequent, and extreme heat. So these are new challenges to the industry. So the modern, the future grids, or even now this is happening, the power generation become more decentralized because now we have, let's say, a rooftop solar system everywhere in the network, right? And therefore, the power flow is not unidirectional as before. And the renewable energy is intermittent, it is not constant generation. And also, use of power electronics in the power grid is increasing. For example, when we integrate renewable energy, so we use power electronic converters with solar panels, right? And in addition to that, we are using HVDC transmission, and flexible AC transmission devices. All these are power electronics. And the power system, when you integrate more and more renewable energy, so the system inertia is decreasing. System inertia means when you have large synchronous generators, so they are rotors, they are turbines, they have a big inertia. So even when there is a sudden change in the load or some fault, some disturbance, that can be overcome because of this huge inertia. But with generation and other sources, because of interface to the converters, that doesn't supply this inertia. So that makes the stability a bigger issue now. Yeah, in addition that now the loads are not like the static loads. Sometimes there are smart loads, like the load demand changes depending on the pricing of electricity, right? Of course, when you have time of use tariff, that means depending on the time of the day, your price will change, and then the load will, the smart loads try to adapt for this change in prices. And in the extreme situation, your prices can change in real time, and then your devices can respond to these changes in real time. So when the grid is becoming like that, we need to need a lot more information to deal with or operate the grid, right? So you need a lot of data, and also you need this data in almost in real time. So what this says is that we need much more advanced real-time monitoring and control a modern grid. So that is where this the wide area monitoring comes into picture, right? So we would like to have some understanding about how a power system status in all of the grid. So the problem with the power grids is the power grids are like geographically very, very spread over very large area, right? And so you need to make measurement at very different locations. And if you want to see the whole system, you need to bring all these measurements to one location, typically the control center of the power system. Of course, in a country like Sri Lanka, we have like one power system, centralized power system. There is one control center. But in large countries like Canada, even in India, so you have many different, let's say, the provincial power utilities or the state power utilities. And they are also interconnected between each other. And then, so this monitoring happen at different places and so on. So in the conventional power system, we still have the concept of wide area monitoring, and that system is normally referred to as SCADA systems or supervisory control and data acquisition systems. So these measurements, these systems receive the data from what they call the remote terminal units. And so this could be measurements and the status signals of circuit breakers and so on. So this system basically scans the data at intervals of 1 to 10 seconds. So if you're talking about, let's say 1 second, 1 second is for a power system is more like a very steady state situation, right? So it's in 1 second, you can have 50 cycles of AC electricity, right? And so because of this measurement time interval, so this provide more or less steady state data. So many of the dynamics that is happening in power systems are faster than 1 second. And the second thing is that okay, the remote terminals measure the data, let's say at maybe every 5 seconds, and send the data, measured data to the control center. So the control center scans, and then whatever the data received at that time, so they are taken as the current data for the current time interval. So the time alignment of data is kind of approximate. It's not very precise. But when it comes to synchronized spacer measurement, and normally we call them as synchro pacers, right? That's changed the picture completely, right? And so this synchronized spacer measurement, they have reporting rates up to 50 or 60 paces per like measurements per second. So that depends on the system frequency. If it's a 50 Hertz, so you could observe 50 measurements in 1 second. So that means one observation at each cycle. And the main thing is that the measurements are time synchronized, and also each measurement is time tagged. So once you receive the data at a central point, regardless of any communication delays, you can time align all the measurements based on the time stamp. And so therefore you can get a very accurate snapshot of the whole big power system. So there are two things. One is the faster reporting rates. Therefore you can observe dynamics, much faster dynamics that you can observe with this SCADA. And also the time synchronization and time stamping, you can get like a very accurate snapshot of the power system. So for example, if you compare some measurements, right? So this diagram shows some oscillations happening observed in a voltage. So this is kind of the forced oscillations just to take the measurements. So if you observe that from the SCADA, what you would see is that this blue waveform that you see here, because you can see now their reporting rate is much slower, right? On the other hand, if you observe it from using synchro pacer measurements, what you observe would be like what this is shown in orange color. Right? So this is a very long time period, but if you expand this one, you will see that this is like basically going to very low frequency oscillations over there. Right? So that's the kind of difference that you can see, the difference between SCADA observations and the synchro pacer observation. Okay. So this technology of synchro pacers was developed in 1980s. The research was done at Virginia Tech in United States by Professor Rajapakse and Graham Thorpe. So by mid-1990s, so there was some prototype PMUs developed, and they were installed on the testing as testing devices in real power systems. And of course, there was some companies who started building commercial pacer measurement units around the same time. And in fact, the first company that built PMUs were like a spin-off from this Virginia Tech research group. So the technology was there, but it was not like a very widely used. But this big blackout happened in 14 August 2003. Right? So the part of Canada and US went through a big blackout. And so the cost of this blackout was enormous. It's billions of dollars. For some places, I mean, they could not recover it from maybe for 1 or 2 days. And for some places, it was maybe up to 1 week. And so then there was a big investigation what happened and trying to understand what causes this blackout. And there's a big report on this, and anybody, I think if you search, you can find out this report. And so in this highlighted the usefulness of wide area monitoring almost in real time. So the basic idea was that if we had proper monitoring, probably we could have stopped this blackout happening. And so this one of the recommendation was to improve the monitoring capabilities using synchro-based measurements. So there's a lot of government-funded projects started as a result of this recommendation in North America, especially. And also they created a special organization called North American Synchro-based Initiative just to promote this technology. So at the same time, the IEEE, the organization that which you belong, so this in the power and energy systems areas, so the IEEE developed a lot of standards. And so there was some working group which started looking at the synchro-based technology, and they start developing standards so that when you have a standard, different manufacturers can come up with commercial devices, because now you know what to expect from these devices based on these standards. So they standard define what should be the accuracy, how should you, let's say, communicate these measurements, and so that the measurements can be issued by different devices, and so on. So all this basically increased the popularity of this technology, and now it is widely used everywhere in the world. For example, in North America, it's more than 2,500 PM. I think this number is a bit old now, it should be much more. So even in China, more than, I think, nearly 3,000, and even in India, so there are nearly 1,800 PMUs looking at the grid. And so these PMUs, they are basically streaming the data, which will be collected and observed at the control centers. Okay, so that's my brief introduction. So why we need this type of measurements, and what is the current situation of technology. Yeah. So next, we look at what are the synchro bases, right? Or maybe are all of you electrical engineering students, or maybe professionals? And I assume that at least you know what the places means, right? So I kind of have to assume that all of you know have done some electric circuit courses and understand what is a phasor means, right? So as you probably have learned, so we define phasors to represent steady state sinusoidal signals, right? So a sinusoidal signal we can define using this kind of equation. So in this equation, we have a number of parameters. One is the amplitude, which is this xm, and then we have a phase angle here, and also this frequency omega, which is equal to 2π times the frequency, right? So we need all these three parameters to define this sinusoid, right? So in the definition of phasor, basically we assume this frequency is constant, right? And so on that assumption, we can define the phase as the amplitude and the phase angle. In the power area, like we use the RMS magnitude, so it would be Xm divided by square root 2. But if it is in electronics or in other areas like signal processing, people, telecommunication, the people use just the amplitude. But in power, we like the RMS magnitude. So you can represent it as a rectangular form, like the real and imaginary parts. On a phasor diagram, we represent it like using a vector on the real and imaginary plane, right?
So audience, please interact with our coach, because you need to ask questions and interact with the coach, because this is a workshop, not a lecture.
Okay, yeah, so if you have any questions, you can ask. Or I think also in Zoom, you can raise your hand too, right? So this basic concept, all of you are familiar, you know. I assume that at least you are familiar with that. Okay. Now, let's say in actual power systems, the signals are not like that. So their amplitude can change with the time. So let's go through some oscillations or some other type of changes. And also their frequency, we assume it is constant, like say 50 or 60 hertz. In real life, it is not constant too. The frequency, if you monitor, if you can measure, you will see it just changing all the time, but changes slightly, but it will remain around the 50 hertz, let's say, but it is actually changing. So if we have a signal like that, we can represent the time domain signal as a variable amplitude, maybe the variable frequency. So you can write it as Xm of t times cosine 2 phi ft dt times phi, right? So the total phase angle is like the integral of frequency. So if you simplify this a little bit as, so this ft is equal to f naught, which is a constant, like our nominal frequency, plus some delta f, which is the deviation. So this deviation could be changing with the time. And then you can write this same thing like this. So here we have your familiar term, right? And if the frequency is constant, so this should be 0. So this part disappears, then that is the same form that we are familiar with, right? And then, of course, if this is constant, then it will be it's not changing. So this represents like this kind of dynamic signal, right? So when we try to represent this kind of signal using phasors, it violates the principle of phasors, because the phasor definition is, okay, you assume the frequency is constant, right? But if you want to represent these real signals in dynamic signals using phasors, so you have to relax a bit that. So we can assume, we can use the so-called dynamic phasor in this case. So in the dynamic phasor, so the amplitude is not constant and also the phase is not constant. So in this case, amplitude would be whatever the xmt, and of course we can divide by square root to get the RMS value. Now the phase angle, so before it was just phi over here, it is a constant, but now, so this part was there, so that is the nominal frequency part, which we ignored because we assumed the frequency was constant. Now, whatever come into this part, we can assume as a change of phase angle. So we can put it as part of the phase angle, right? So now we have a phasor, which is of this frequency f naught, but now with the changing magnitude and changing phase angle. Of course, if delta f is a constant deviation, then you can simplify this as just like a delta f times t. But typically, in real life, this is not a constant, this is changing with time. So now that is the pace of a change in signal, right? But what is a synchro pacer? Right? So in a circuit, when you are using a pacers to analyze, you take one pacer as the reference and then define the pace angle of other pacers with respect to that particular reference pacer, right? So here also we use the same idea. We define a reference cosine signal, right? And this sinusoidal or the cosine signal has exactly the system frequency, 50 or 60 hertz, depending on the system frequency. And so it has a constant frequency. And the second thing is that, so the peak of this cosine signal coincide with the beginning of the UTC segment. The UTC is called the universal coordinate time. That is the time standard that is used in the worldwide. So whenever a new second start, so that point coincide with this cosine signal. So if there are like a 60 or 50 hertz, so after 50 cycle, when the next second begins, so it should coincide with the beginning of next second too, if everything is correct, right? So then any other cosine signal, the pace angle of any other signal we express with respect to this reference cosine signal, right? For example, this red color measured pacer. So there's its peak occurs at this point. So there is some time difference between the peak. Of course, the time difference we can convert into a pace angle difference, right? Based on the frequency. So this pace angle, which is measured with respect to this the blue one, which is the reference pacer, then we can call it is a synchro pacer, right? In the imaginary real plane, so reference pacer always coincide with the real axis; it doesn't change. So the measured pacer, which will have some pace angle depending on its phase shift. And its magnitude, of course, it depends on the actual magnitude of the signal. Typically, the reference pacer has a magnitude of 1. It doesn't really matter because we need this reference signal only for taking the pace angles, right? Now, why do we need to consider this absolute, like a time preference like this UTC? That is because, so when you observe like a wide area, so our measurement devices are not at the same location. So they are at different places, right? And of course, all these like modern microprocessor-based devices would have an internal clock, but that internal clock is not always synchronized with the, let's say, universal UTC. If it is not synchronized, they will have different times, right? Even if you synchronize, let's say at the very beginning, these clocks start drifting with the time. And so after a while, so they will be having different times there in their internal clocks. So if we use the internal clock of each device to generate this reference signal, then when you calculate the pace angle, so they are not with respect to a common reference. So that is why we need to adhere to this UTC. So this UTC is basically, it is the standard time, or the absolute time reference, we can call it. This time actually is basically very closely related to the Greenwich Mean Time. So it's equal to the mean solar time at 0 longitude, which basically passes to the Greenwich time. And it is accurate to about 1 second compared to the solar time. The solar time is basically the time that you compute based on the position of the sun, right? At solar noon, at 12 o'clock solar time, the sun should be directly overhead of you. Of course, how do you keep the time is based on the International Atomic Time, which is basically the average of, I think, more than 200 atomic clocks located all over the world. But there's a difference between the what they call the TAI, or the International Atomic Time, and the Universal Coordinate Time. That is because the Earth rotation is not constant. Sometimes accelerate. And recently I saw a newspaper in 1 or 2 days before. Actually, it typically slows down, but recently it has started rotating a little bit faster. So what does this mean? That means you always don't have a 24 hours for your day, right? It changes. And in that case, you need to add on you call the add or subtract leap second based on this one time to time. So it happens occasionally once in a couple of years, right? So these two are slightly different, but they are very closely related, right? So as you mentioned, so the phase angle is defined as 0 if the maximum of cosine signal occurs at the beginning of every UTC second. So this is called UTC second rollover, right? And typically we get this signal from satellite clocks, which use the GPS signals. And satellite clocks generate what we call the 1 pulse per second. So at the beginning of every second of UTC, it issues a 1 pulse. So this signal we can use to synchronize our local devices with the UTC. Okay. So now we have a little bit of understanding about what is a synchro pacer, right? So, once you synchronize with that UTC, so regardless of the location that you measured, you have the same phase angle reference. So that is the idea of synchro pacer, right? And of course, in addition to the magnitude and phase angles, synchro pacers also measure the frequency and the rate of change of frequency. So according to the standard, the frequency is defined as the rate of change of phase angle, right? And of course, if you go back here, so for the phase angle is like a part of the phase angle. So if you take the derivative of that, it becomes basically the frequency deviation, right? So using the same definition, you can use the same definition to compute the frequency. And of course, the rate of change of frequency is the derivative of the frequency. So you can basically use those definitions to compute frequency and the rate of change of frequency. Typically, the frequency can be reported as the frequency or the frequency deviation, because the nominal frequency is always known. Yeah, so how you report the synchro paces? According to the standard, you can report either as real and imaginary parts or magnitude and phase angle, right? But if you're using the phase angle, your angle is reported in the range of 180 minus 180 to plus 80, 180 range. And of course, the measurements should be reported at one of the standard rates. And if it is a 50 Hertz system, so you can report at 10, 25, or 50 paces per second. So this is called the frames per second, FPS. If it is 60 Hertz system, you have more options, 10, 12, 15, 20, 30, or 60. So the idea is that you try to report integer number of measurements in each complete second. And of course, there are devices which can report higher than, for example, in 60 Hertz system, you can report 120 or 240 FPS. The PMUs are there with this capability, but the standard only say, okay, up to this much. Now, look at what happens, our measured signal is not exactly 50 Hertz or 60 Hertz, right? So our reference signal, reference cosine function, we define it assuming it is a 50 Hertz or 60 Hertz, depending on the system. And so its frequency, the signal is different. For example, let's say nominal frequency is 60 and actual frequency 61 Hertz. So if you, let's say at the beginning, both of these signals had a 0 phase angle difference, so they both have the peak at the beginning of the second, right? Now, the yellow one is the reference papers, which has 60 Hertz, but which has a 61 Hertz would be something like that. So as you go on, you can see that the zero crossing points or the peak points start to deviate, right? So if you're measuring the phase angle with respect to the reference paper, so what's happening is that as the time passes, your measured phase angle will actually start to change. And then that is quite normal based on our definition, right? Because so when there's a deviation, so this part will start accumulating, right? And therefore your phase angle is supposed to change if the frequency is not exactly the nominal frequency. And so if you start observing a synchro phase measurements from a signal which has a frequency not equal to the nominal frequency, it will appear as kind of having a changing phase angle. For example, the deviation is constant in this case. So if you are reporting as, let's say, 12 measurements per second rate, so in 1 second you will see 12 measurements coming. And at each measurement, you will see this will be shifted by the pace of the signal will be shifted by 30 degrees. So after 12 measurement, it will again come back to the 0 phase shift. Of course, in real system, you rarely observe this kind of constant phase deviation. You would see something like this for your phase angle. Now, what is happening over here? You can see because the phase angle is frequency is different, your phase angle will start changing, right? So here what happens is that when it is come to 180 degrees, so it will not, it is actually keep on increasing, but when you are reporting, because you have to report between -180 and +80, so next one you do report as -180 and then goes on so on. So these sudden sharp changes are because you are changing, you're limiting the frequency, like the report angle range between these limits. So like if you take somewhere like this in this one, so here the phase angle remain almost constant, and that is because the signal frequency and the, it become equal to the nominal value. So if when it crosses the nominal value, so at whatever the phase angle that you start observing, it will remain constant. And of course, if it changes, like if you start decreasing now, it changes in some other way, right? So this is something important that you have to remember. And also if you're comparing the phase angle difference between two signals, because of these changes, maybe that phase difference, which may be very small, and it could, when this change happened, you would see like a really, really large difference suddenly. And that is not something wrong, but that is because we are changing the reference for the phase angle reporting. So these are some normal things that you will observe. Of course, when you have any measurement system, so we have to worry about the measurement errors. Since we are measuring phases, which has magnitude and phase angle, we can regard the measurement as a vectors. So in this IEEE standard, actually, it uses a clever way of reporting the measurement. Instead of limiting, giving error limit for the phase angle and the magnitude separately, it defines what we call the total vector. So the definition of that is, let's say this is the actual phase, but your measured value phase is something like this red one. So the error is the vector difference between these two vectors. So that is the delta x. So its magnitude is called the total vector error. So in the equation, you can define it like this based on the real and imaginary part of each of these vectors. So quite often there's a limit for the TV or the total vector error. And so this limit is, let's say, typically 1%. So this 1% limit, actually, you can define some like a circle like this. So this is the end of the actual vector. So any point within this circle, which has a 1%, so this is actually kind of a little bit enlarged, but if you draw 1% of this one, so if your measured vector lies any point within this circle, so it is accurate enough. But if it goes outside, then it is accuracy is not within the defined limit. And to get some understanding about how tight the accuracy is, so this 1% TVE can result from, like, even if this red line is coinciding with this one, but if there is a error, 1% error in the magnitude, so that is 1% error. On the other hand, if you have the same magnitude, but if you have a phase angle difference of 0.573, then it is exceeding the 1% error limit. So this phase angle error is actually corresponding to 31.8 microseconds timing error for 50 Hertz. And for 6 years, it is even less than that. It's a 26.5 microsecond timing error can result in this error. So if you are building a PMU device, so your time synchronization need to be very, very accurate if you want to achieve the this kind of accuracy level. Of course, I mentioned about standards, and many of the definitions that I presented to you are coming from these standards. And the first IEEE standard was called Synchronous for Power System, And it basically defines the time synchronization by basically doing the synchronizing the sampling times with the UTC. And that was called IEEE standard 1344 in 1995. But so this standard was revised in 2005, that is after 10 years. So normally the IEEE standard has like a 10-year life cycle, or actually 5-year life cycle. And so it was changed. Now this is the standard which introduced the total vector error and the performance requirement like based on the total vector error. So it basically do away with the synchronizing using the sample timing synchronization. And also it give a clear idea of how to communicate these measurements. So it was again revised in 2011. And by this time, this was divided into two parts. One is for the measurement, other one is called the data transfer, the communication part of the standard. So this one tried to deal with the communication protocols, and the first part deal with the measurement part and define the accuracy and also the dynamic performance of requirements of these measurements. And this standard is actually now has become joint IEEE IEC standard. It's called 6225.1181 of 2018. And that is basically the measurement part. And the new standard is coming for the joint standard is coming for the data transfer part too. And of course, then there are guidelines and some other data concentrator requirements, the communication. And of course, this is IEC standard. So the IEC has a different standard for communication. And that's there's a part of that standard which deal with synchronous communication using this IEC 61850 substation automation standard. And of course, the timing standard, IEEE timing standard 1588, which was a precision time protocol, can also be useful for synchronous measurements because your time synchronization can be done using this precision time protocol as well. Okay, next we look at how can we use this, how can we build a measurement system using these phase measurement units, right? So if you have a power system, your basic measurement system, which you call the phase measurement units, are installed at substations. So in the substations, you can have multiple PMUs, and the data from these multiple PMUs are collected by a computer called Pressure Data Concentrator, or PDC in short. And this PDC collects the data from maybe multiple PMUs and then time align, and it creates some output, which can be sent to another PDC at a higher level, which is called a corporate PDC. So you can have multiple substations with local PDCs, and all of them may be sent into a data to a central station through a communication, a wide area communication network. So inside the substation, you can have a local area network connecting these PMUs to the local PDC. And sometimes the PMUs can be directly connected to this wide area network as well. Typically at the corporate PDC, you collect a lot of data, and then you need to store this data for recording purposes or data use. And sometimes you might be sending outputs to like even higher level PDCs. So if you look at each of these devices, the basic measurement unit is called the PMU, right? Basically, the PMU, it takes the analog voltage and current waveforms as inputs, right? And do the synchronous estimates. So in order to do the estimations, to synchronize, basically you need a timing signal from a GPS clock, typically which use a satellite, GPS satellites for getting the time signals. And then this PMU will publish the measured data to a network, right? So it provides the paces of the measured voltages and currents, and also frequency and the rate of change of frequency. And also it can calculate other information as say real and reactive powers. And also, since you are sending a message with measurements, you can also include other data such as maybe circuit breaker status signals and so on. So the PMU is basically a function, and it could be a standalone device, or it could be just a like a function in a protection relay or a fault recorder, or it could be a function in a meter. So there are many ways which you can implement PMUs. Right? Now, a lot of the protection relays come with this PMU functionality as something that you can enable if you want. Right? So if you look at the function model of a PMU, right? Of course, you need to take analog signals, currents, and voltages. And also you need the signal from a GPS receiver. So as soon as, since all this processing happens in digital domain, so you need to sample these analog inputs. But before sampling, typically you have to do some anti-aliasing or filtering. And then to remove the high frequency noise. So one thing that you can do with this A to D conversion is, so when you're sampling, your sampling instant can be synchronized with your timing signal, or with the, let's say, 1 PPS signal. And sometimes you can have what they call the decimation filter. That means like you sample at a very high rate and then you downsample it for doing the basic calculations. So here is what is happening with the phase estimation. And also we need to do some sort of filtering, which called the, depending on the accuracy class requirements. So after that, you can use the phase angle measurements to compute the frequency and the drop off. And so when you calculate the frequency, if the frequency is not exactly at the nominal frequency, typically you need to do some correction to the estimated magnitude. And that magnitude correction is applied here. And then all those information is passed into the for time stamping and computing the formatting the output for the communication. And sometimes, of course, in power system, you have phase A, B, C, but you can report them as positive, negative, and zero sequence components using the symmetrical component transformation. So it's up to you how you want to report them. And so I mentioned that, okay, it takes the analog measurements, but it could also be the sample data from IEC 621F50 compatible merging units. So those are available in like what they call digital substations. So instead of directly connecting analog signals, so these merging units basically digitize the signal and then send the digital samples over network fiber optics to the relays. So you can use these sample values too. So the pace estimation, there are many algorithms, right? Mostly use the discrete Fourier transform, and also there are some other, let's say, optimization-based algorithms and so on. Some of them are very complex, maybe difficult to implement in real time, depending on your resources. The problem is that many algorithms work very well at the nominal frequency, but the problems arise when the frequency of the actual measured signal changes. And also you can have errors because the actual signals can have noise and harmonics, and also especially the currents, they can have a DC offset values, and these also introduce some errors into your measurements. And many of these measurement algorithms are usually window-based algorithm. That means you take data window, the sample window of data samples, and then you calculate the estimate the phase angle and the magnitude. Now, how do you do the timestamps? So you get the data window.
Excuse me, sir.
Yes.
We have a question from Nadun Chamikara. Yeah. He's asking, how does the CT and CVT accuracy affect to the PMU accuracy? Further, in large network, we can't ensure the same type of accuracy class CTs and CVTs are used.
Yeah, so in the PMU standards, so the accuracy is defined based on whatever it receives at the its input, and then you can compute the phases based on that. And so with respect to whatever the signal that you received at its input, then you had to calculate the phases under that required accuracy. Of course, if your CT and PTs, they have errors, and that will reflect in your measurements, right? And so that error cannot be, I mean, if you know the errors, then you can probably compensate for that. But that is some error happening outside the phase measurement unit. And the impact of that error depends on the application that you are looking at. And for some applications, those, because all these CTs and PTs, they also have some standard accuracy limits. And of course, there are different classes and have different accuracy limits. And so based on that, you will get some accuracy for your measurements. And of course, CTs and VTs you can calibrate, and then you can minimize the errors. And of course, that error is happening outside the phase measurement unit. And its impact depends on the application that you are looking for. And for some applications, these errors are really, really critical because, for example, if you try to estimate the line parameters, if the CT-PT errors are large, then you get wrong result. And I think you will be going to hear about that in some other presentation. Yeah, that's an important thing too. That's a good question, okay? So next, how do you assign the timestamp? Because when you're estimating the phases, you take a data window, right? So the time of the data window at this point and the time at this point are different, right? So what should be the timestamp? And typically, in most cases, you take the center of this data window as your for the purpose of timestamp, right? And the standard doesn't say, okay, the center of the data window must be this timestamp, but what it says is, okay, you have to meet the accuracy requirements, TV error limit. So the manufacturer of the device can adjust your timestamp to as required. But it is typical to have it at the center of the data window. And how you report the time is that you report it as the second of century count plus some fraction of second. So second of century count changes at every second because it's start counting from January 1st, 1970. So it's counting every second. So you have a certain number for every second at the beginning of every second. And then how far your data window from the start of that second is reported as fraction of second. So in the timestamp, you have this SOC plus fraction of second, okay? From that, you can figure out what is the absolute time. So for the time source, I already mentioned that most of the time we get the GPS clocks as the timing sources, but also you can get the time from the network as from using the PTP. But of course, even for the network, you need the master clock, which is basically GPS-based clock. And of course, there are some other standard, maybe there's a Russian system or Chinese system, which are GPS, similar to GPS, but they have different. Even there's a European system called Galileo and so on. You can use any of these systems. One thing to remember is that satellite-based time sources are vulnerable to interference. So they can be affected by solar activity or maybe faulty electronics. And sometimes they could be jammed. Your signals can be jammed. And sometimes some simple things like, okay, the birds can come and sit on a GPS antenna, then they just start giving different things because it cannot see the satellites. So that kind of things happen. But quite often the satellite clocks, they have a very stable internal clock too. So it can maintain the time without drifting for several hours with the required accuracy. And then the measurement compliance. So all these measurements can be reported or can meet two different type of accuracy requirements. One is called the P class accuracy, the other one called the M class accuracy. So the P class is for applications which require very fast response. So it has less filtering, but more error in the measurements. On the other hand, M class is for which need high accuracy of measurements. But because when you try to achieve high accuracy, then you need more filtering and therefore the response is slower. So which class to use, it depends on your requirement of your application. And most of the time, I have seen they use P class, but again, it depends on the type of application that you need. So in this standard, it defines what kind of test you need to verify the accuracy. So the accuracy limit depends on this P and M class. Typically, M class has more strict limits. So I suggest maybe if you have access, you can look at this the standard, then you can see all these error limits and the test and so on. So if you go back to this system, so you have the PMU which we looked at, then you have this so-called PDC, and so this is The function of this is to aggregate the data coming from multiple PMUs, right? So this data may be coming from using different protocols. And this data concentrator, so it collects all this data and they align the data based on their time tag, right? So once they may not be coming at the same time to the PDC because of the nature of and the distance of their measurement units from the PDC. But by looking at this timestamp, you can create a coherent set of measurements. And sometimes you may not even receive some data packets may be missing, and then in that situation, you still create an output. But maybe when you have missing data, you do a flag to say that, okay, there is some missing data here. So a PDC can align the data, and then you can either store or maybe send to another PDC. And of course, there are a lot of other functions happening in the PDC, like checking for any errors, and also it computes like the latency, and there are many other functions, but main function is like aggregating and creating outputs. So as I mentioned before, so these PDCs could be at different hierarchies, at substation, utility control area level, and reliability coordinator level, and so on.
Excuse me, sir.
Yes.
We have another question from Tejal. She's asking, can we use GNSS instead of GPS?
Which one?
Can we use GNSS instead of GPS?
What is TNSS?
GNSS.
Oh, GNSS. Okay, yeah, you can use. But of course, then you're basically, you need to have a satellite clock designed to that one. And the satellite clock, most of the commercial PMUs, they can accept what they call the IEEE signal. And so whatever the system the satellite clock uses, if it can provide those timing signal to the PMU, then that can be used.
So another question from Nadun Chamikara. Could you tell us an example of P-class application?
The P-class application, so if you, let's say if you're looking at, let's say frequency stability, or it's a transient stability type of thing. So that means when your sudden disturbance happens, then we are looking at how the frequency change, maybe how the phase angle changes, and so on. So the transient stability, frequency stability, these things happen within maybe in a less than 1 second, and or in several seconds time period. So you probably want to observe these things without much delay. And maybe then you need to use P-class ones. On the other hand, let's say something like, let's say long-term voltage stability, or if you want to, or estimate maybe even, let's say, estimate the parameters of a transmission line or other network parameters, then you are more interested in the accuracy. And so these parameters will not change suddenly, right? They could change with the temperature and so on, but they will be changing much slower. And then you can use M-class measurements because you need accuracy, and your phenomena that you're looking at is not changing very quickly. I hope that clears your question.
Thank you, sir.
Okay. So the next part is the communication part. Okay. So as I mentioned, so there is in the 2011 standard, there's a part of for this synchro as a data transfer. I think now there is the updated one, which is the IEEE joint standard for transfer of power. I haven't seen that one yet, but I think it is already out. So this defined a method for exchanging the data between from measurement unit and a PDC, and also between two PDCs, or with between a PDC and other application, right? So this is an open access method. So that means you should be able to communicate from the device from one vendor to a PDC from a different vendor. So there is nothing hidden. So everything is very transparent. So this is called interoperable between different manufacturers. So it is a very simple direct method of data transmission, and the structure of the data packet is defined in the standard. And actual communication, you can send it as using a TCP/IP or TCP, so UDC/IP, or even serial communication and so on. The standard define only the part of the payload. And there is also this IEC standard that I mentioned before. So it is using IEC 61850 communication. So for this one, I mean, it's a bit harder to explain IEC 61850 because it's a very big standard for like modeling and communication substation functions and communication. So it's defined what we call the logical nodes for different functions, like a protection functions, measurement, and so on. So in this case, PMU comes under measurement logical node. So it defined the characteristic of this logical node in this standard. And so the data can be communicated using what they call the RGOOS, or the routed GOOS, or routed sample value protocols defined in this, the latest version of this standard. So how this communication happens, there are three types of data frames. So one is actual measurement data, and so one in the frame called configuration frame, and the other one is called the header frame. And also there is another frame called the command frame. So all these are needed to do the proper communication. So it happens is quite simple. Usually the PMU is like a server and the PDC is a client. So the PDC send a command frame, so asking to send a configuration frame. So then the PMU send back the configuration frame, and then the PDC knows, okay, what is this PMU is going to send back. So how many paces are there, the format of the paces, for example, whether it is reporting real and imaginary or magnitudes and angles, all this information is in the configuration frame. So once we know the configuration, the PDC send a command frame asking to start sending the data. Then it will start sending data frame. So once we know this configuration, the PDC can decode these data frames. And when it wants to stop getting the data, you can send in the command frame asking to stop sending me the data. And so this is the way of communicating. If we use the IEC mode, and then so this is actually called a MMS request. This is called multimedia message or something. I don't remember exactly what it is. So similar thing happens, but the way that the communication sending would be slightly different. The protocols are different. Okay. So if you need to, for this system work, so your communication network should have a low latency and a sufficient bandwidth to send all this data. And of course, it need to be like a reliable, resilient, and flexible when some, say, faults happen in the network. It should not seriously affect the functionality of the communication, like the pressure measurement system. Of course, there are, when you talk about the latencies, so there are different latencies. There's some latency in the PMU, because when you're doing the measurement, there's a time delay over there. And in the network, there is a transmission delay. And then also in the PDC, there are certain time delay and so on. So all these need to be considered when you are designing the applications. Of course, another thing is that cybersecurity, because we are using the network for transferring the data. And sometimes this data could be used for important control purposes and so on. The one problem is that this particular standard, the IEEE standard, does not support any security approaches over there. So you have to provide the security externally. And typically it uses firewalls and so on, which actually increase the latency of this communication. But if we use IEC 61850 90-5 protocol, it has certain inbuilt security features compared to this IEEE C37.118. So somehow in North America, so there's something called North American Electric Library Corporation, or the NERC. So it has certain standard on cybersecurity. So all the North American utilities need to follow these cybersecurity standards. So the CIP, or the critical infrastructure protection standards, are those applicable to cybersecurity in at least in North America. Okay. How much more time that I have?
You have another 45 minutes.
That's good. Any questions so far?
Yeah, Sajid Paulus raised his hand. Hi, Sajid.
Yeah. Good morning. Can I have a question?
Sure.
Yeah. Yes, Professor. Now you mentioned now we can get current and voltage data to PMU using this merging unit using 61850 sample values. Normally, these sample values are timestamp. Therefore, we need a separate time synchronization for this PMU also.
The I61850 sample values sort of not they are some sort of like a time synchronized, but they are not exactly time stamped. So they don't have a time stamp like the one you have with the what you get with the synchropaces. But I think there's a sample count which indirectly you can use as a kind of time step, as I understand. But for the pacer calculations, you still need to have its internal reference for generating the reference signal, the reference cosine signal, and so on. And also, it need to do the time stamping and everything. So you cannot completely rely on the time. It doesn't have actually like it has some sort of like a time reference, but it's not like a time stamp. It doesn't say what is the second of century or fractions second. That it's not like that. I think it has a sample count which you can maybe use to relate with some time. So because of that, I think you cannot simply rely on that time stamp or the sample count of the IEC 62850 sample values.
Yes, thank you, Professor. I have another question with regard to same configuration. Now this PMU also have a sampling rate, and this merging units which transmit sample value also have a sampling rate. How we need to match these two sampling rates?
Oh. If you are getting the sample rates, you don't have to like a resample inside the PMU because you are directly getting the samples, but you may have to downsample the things because, for example, a merging unit would send like 80 samples per cycle, which is probably too much for synchronous estimation. So you can actually probably do some sort of downsampling over there.
Yeah, thank you very much.
So in the next, let's say, in half an hour or so, I will try to go through some of the Phas estimation algorithms, and mainly I will focus on the discrete Fourier transform Phas method, and maybe I will just don't explain other methods, but I will just mention what are the other possibilities. So especially if you are like trying to design a PMU in a competition, so you need to probably understand some of these algorithms. Yeah. I think this slide we already had a look at. So we mentioned that there are many different algorithms, many possible algorithms. So we will first look at what we call the Dft Base Methods. Okay. So I assume that maybe you have probably taken some maths course or signal processing course which deal with the Fourier transform and so on. I'm not a signal processing expert, so I'm basically a power system engineer, but maybe you are probably more familiar with this stuff than myself. So if we look at what is DFT, right? So it's basically, you can say it's as a method of calculating the Fourier transform of a small number of samples taken from a signal. Right? So if you have a continuous signal called xt, right? And if you sample and take, let's say, n number of samples, so we can, with these sample values, we can write it as another function, let's say yt, which is basically sampled at delta t times. And we are considering n samples from 0 to n minus 1. So this simple n changes from 0 to n minus 1. So to get the sample in the signal processing, you basically multiply your time function with the delta function to get the samples, right? So it's a sum of some samples. To obtain the discrete Fourier transform, right? So for any time domain signal, you can apply or you can get its Fourier transform, right? So if you consider this as a time function, of course, it contains samples, but it is a time function. So if you take the Fourier transform, you get a frequency domain function, so let's say YF, right? So this could be a continuous function in the frequency domain. It depends on what this function is, right? So it is a frequency domain function, but in the discrete, like it's a Fourier transform. Like although you start with the sample value, it is a Fourier transform, so it could be a continuous function in the frequency domain. To get the discrete Fourier transform, you sample this one also again in the frequency domain. So you have the step in the frequency is 1 over T naught. So T naught is basically the time corresponding to this n number of samples. So that is equal to n times the delta T that you have here, right? That is basically if you trigger this as a window of samples, so this is the window length in time. So 1 over window length is the frequency times frequency step at which you are sampling this YF function. So that you can write it as YF. So you can sample at delta F intervals. So these samples could be from minus infinity to plus infinity. Although theoretically this goes to from minus infinity to plus infinity, actually there will be only n number of distinct values for the phi f. And so these values you can compute like this. So this is basically the application of the definition of Fourier transform. That means you multiply this signal by this value, right? So this K in this one, so this corresponds to different frequencies, and it's changed from 0 to n minus 1 if you start with n distinct samples in the time domain signal. So when you calculate those, let's say, so n frequency, like frequency domain values, and it is actually symmetrical about n by 2. So basically you can treat any component, frequency component beyond n by 2 times delta f belonging to so-called the negative frequency. Because it doesn't calculate frequency component beyond half of the original like a base frequency, because we want to follow the Nyquist criterion to avoid aliasing errors. So you compute n number of values, but half of them are considered like it is the same values, like half of them are same as the previous values. So this the second set we consider as a negative, corresponding to the negative frequency. So of course, if you want, you can use the inverse Fourier transform to recover the original time domain things. So if you apply inverse Fourier transform to this frequency domain function, you can get the original samples that we start with in the time domain if you want, right? So that will result in n distinct values in time domain. So that's the Fourier transform, or that's a DFT. Now let's consider the Fourier series, right? The Fourier series we can use to represent periodic function, right? For example, in the power system, we use sinusoidal functions, and therefore we can use Fourier series to represent, because they are periodic, right? So in a periodic function xt, so in this case, the periodic function you can write as sum of complex exponents. So this is the exponential form. And this is the coefficient alpha n corresponding to like this n change from minus infinity to plus infinity theoretically. And each coefficient you can compute if we know this signal. So that is the signal multiplied by this factor integrate over one period of the signal, because this is a periodic signal, right? And then you divide it by 1 over t, which is the periodic time. And this n can change from 0 to plus or minus 1 and so on, because this goes from minus infinity to plus infinity. So if you consider the sample signal, right, that means you have x exists only at delta t intervals. Then you integral, which you write here, you can represent as this alpha value. You can compute as a summation like this. So that is the sample multiplied by this value. So this depends on the k as well as this n, which is the sample number, right? So this t, the t is now equal to n times delta t, because you have n number of samples per the one period of the signal. So you can a little bit simplify this one, and you can write it this way. So this delta t will cancel out with delta t. So 1 over n times this summation, right? Now, if we look at our Dft, which we defined before over here, right? So this part, right? So this is, if you consider this part and compare with this Fourier series coefficient, so there's, you can see some relationship between, right? So this summation part is exactly the same over here, but then you have this 1 over n in the Fourier coefficient, which is not present in the Dft coefficient. Of course, your coefficient exists from 1 to n minus 1. Yes.
Excuse me, sir. There's a question from Tejal. What is the difference between Dft and SDft technique?
What, FFT or D?
Dft and SDft.
FTFT. What is FTFT?
SDft.
Is it in the chat box?
I think, yeah, I'll put it in the chat. It's she has.
If the person who asked the question what it means, if you can define what is FTFT.
SDft. Tejal, can you speak? Hello.
Hello. Yes. Yeah, you can go ahead.
Slide in Dft.
Slide in Dft. Yeah, I think maybe, yeah, probably we are here talking about sliding Dft. Means maybe because with Dft you need n samples, and it's like taking a window of samples. If the signal is continuous, we can shift this usually in our computations, like especially in this type of continuous signals, we then shift this window by one sampling until we can compute the next set of Dft values and so on. When you continue this one, you can call it a sliding Dft. I think maybe this is what you probably mean. Otherwise, you can just take any stationary data points and then you can apply this Dft to. In actually this kind of like in synchropressor, like in a PMU, actually you want to do this is with the signing window in a continuous fashion. I think we come to that point maybe sometime later. Okay. So now if you look at this correspondence, what we can see is that we can get this alpha k values from the Dft coefficients, right? So what it says, you can get this alpha k by dividing the Dft by n. Again, so although theoretically it has minus simply possibility, you will only have n distinct values. And in this case, k equal to 0 would be x0, and that is the DC component. And then your k equals 1 will be your fundamental component. Let's say fundamental component means if we are dealing with, let's say, 50 Hertz signals, so you design your data window to cover one cycle, and then your fundamental would be corresponding to 50 Hertz. And the second harmonic would be 2 times that, that is the 100 Hertz, and so on. So, and of course, so this is k equals 1 is fundamental, but and also k equals n minus 1 could also is corresponding to the same frequency because of this symmetrical nature, or basically we are treating this as negative fundamental, negative 50 Hertz or something. So it goes in a similar fashion, like k equals 2 and k equals n minus 2 corresponding to the same frequency. So when calculating the Fourier series coefficient, so we need to consider both negative and positive frequency components, right? So if we are trying to obtain Fourier series coefficients from Dft, we can use this relationship. For example, A0, which is corresponding to DC component, would be 2 times the 0 component of the Dft. So AK, which is the real part of alpha k, would be real part of XA. Remember that when you take the Fourier transform, the output would be a complex number. So it has a real and imaginary part. So this you can compute both real and imaginary parts. So you can from 1 to n minus 1. So this 2 is basically to take into account we have both negative and positive frequency parts. So if you have a time domain function as AK times cos this one and plus BK times this one. So this is a periodic function, right? And of course you can write it in this form too as a cosine function with some phase shift. So this phase shift is like this, depending on BK and AK. So its frequency is F0, right? So if this is like a sinusoidal function like this, right? So we can represent it as a phasor, right? With its magnitude would be this divided by square root 2 because we are looking at the RMS value. Or if you're using a real imaginary way, then you can use AK and BK directly, like this divided by square root 2, and this will be the imaginary part. And of course, the phase angle will be this value. So this is the exponential form of the phasor. So you can see the relationship between if our original signal is a periodic signal, now we can see a relationship between the Dft and its amplitude, right? So for the frequency coefficient of the Kf0, so this K is changing from like a 0 to n by n minus 1, right? So you can compute the phasors corresponding to different frequencies, either in the like using these equations. Right? So basically, in the power system, mostly we are looking at the fundamental component, because depending on the number of samples that you consider for one cycle, you can get multiple frequency components. That is the fundamental plus its harmonics, right? But so number of harmonics you can calculate depending on your frequency, like a sampling frequency, or the number of samples per cycle. But if you are not interested in all these higher frequency components, which is the case in this situation, because we are looking at the fundamental patient, right? We only want to compute X1, which is the fundamental component. Then you can simply compute your real and imaginary parts like this. So X, these parts are your sample values of your original signal. And then you have this multiple, the cos and the sine functions to get the real and imaginary parts of your phase. So when you apply this Dft method for phase estimation, what you do is you get the data window, typically like one cycle. So you have multiple n, let's say n number of samples. Start from 0 to n-1. So each, so you can see the sampling frequency is equal to n times f0. So f0 is the original signal frequency, let's say 50 or 60 hertz. N is the number of samples per cycle. And also the time difference between two samples, in this case, delta t. So we can represent that as a phase angle too, right? Because based on this f0, so this data window is corresponding to 360 degrees or 25 radians. So the phase angle difference between two samples, you can say 25 divided by n, because we have n samples per cycle. So you can write this signal, actually, the sample signal as xn. So this xn is each of these n changes from 0 to n-1 as cos n theta plus the original phase shift, which we had over here. Right? So we have n number of samples ranging from 0 to n-1. And now with these samples, you can compute real and imaginary part using the formula that we have. So this square root 2 comes from 2 divided by square root 2 to take the RMS values, and this is n over here. So xn times cos n theta, because so these cos and sine parts coming from the definition of Fourier series, right? And then once you have this real and imaginary part, your phasor would be real part plus j times imaginary part. I mean, in this equation, you can write in the exponential form by combining these two as a complex number. So cos n theta plus this j sine n theta, you can write at e to the power j theta. So sometimes we use that convention too. So in this case, what is happening is that you have this cos n theta and sine n theta parts. So when n equals 0, that is at this point, when you're at the first sample point, so that it is cos 0, that means this we can regard as a sort of like a reference cosine function. So it happens its peak coincide with the first sample, right? And similarly, this can be regarded as a reference sine function, and it's the first sample is its zero crossing point, right? And, so we define the reference cosine sine signals with respect to our data window that we consider here. The calculation that happens, as you can see, is very simple. So if you have the function that you are measuring, you sample it at your sample interval, and then you have two functions: the cost function, reference cost function, and the reference sine function. So in this particular example, our cosine function has a peak coinciding with the first sample of this one, and the sine function sine zero coincide with the first function, right? And we basically multiply these samples by these sample values and so on, and take the summation, and then we multiply this factor square root 2 divided by n, and that gives the imaginary part. If you take the product, sum of the product between the sample values and your cosine samples, you get the real part. So it's very easy to compute the paces. Of course, now if you take one set of samples, then you can compute this, that is fine. But in a PMU or protection series, we need to do this continuously, right? So you have to repeat this same calculation after taking a new data window, which may be shifted by one sampling point, right? So if you compute the first phase, so we will, let's say, get this one based on our definition, right? So this is I put the cost and sine parts together over here. So when you compute from the next window, you get this one, right? Now, what happens is that because when we shift the window, we always start our reference cost and sine function at the beginning of the data window, or the first sample in that particular window. Which means we basically shifting our reference at each new calculation. Therefore, when you look at the phase angles for these things, even if your magnitude is constant in this measured signal, you will see your phase is shifting by a certain angle, and that angle is actually equal to this theta, because that is the angle corresponding between like one sampling interval. And that, because you are shifting your cos and sine reference signals, you will see the phase angle as always changing from one step to next time step and so on. So when you're doing, let's say, continuous calculation, this is not a good thing, because you will see that this change. So this is not due to, like, even at a fixed frequency, you will see this one, because we are shifting our cosine reference function. So if you're using this method of calculation, you typically want to compensate for that one. So you have to give a minus phase shift of theta every time that you compute. So you can compensate externally after computing, because we know the sampling interval exactly what it is. The other option is maybe you change your calculation method and you use a recursive type of calculation. So how this works, you can easily prove that, okay, these are the things that we considered in the previous page. If you put these two together, you can write in the exponential form with e to the power chain theta, which is equal to the same part, and so on. So in this case, so this after shifting this is a different, because now new set of samples are shifted by one sampling point. So the results of these two will be slightly different. But if you multiply the equation for like this one, xn by e to the power minus j theta, so you get this kind of thing, right? And also, because n times capital N times theta is equal to 25 degrees, right? So actually, not this should be e to the power theta. J theta should be equal to e to the power minus j n theta. So if you use this equation, then you can actually write this new Phasor should be the old Phasor plus this quantity. So this is the new sample coming in, and you subtract the previous sample, the original sample that we had in the first calculation, and you multiply by this. Actually, this should be 1 theta, not 0 theta. Maybe this is correct probably, but other one should be changed. So now, if you once you compute the first one, and then you can second one, you can compute very easily considering the new sample and the last sample and this theta value. So in generally, like xn plus r, that is after r sampling points, you can compute if we know the previous magnitude of the previous Phasor, plus then you multiply by at this part, you add the new sample and remove the older sample from this calculation, and this difference multiplied by this one, jr theta. So you can represent this as a recursive algorithm. So it's quite easy to implement in a digital computer. Of course, if you don't want to compute these exponents, you can compute as real and immediate parts separately using cos and sine values. Okay. When you use the recursive methods, what happens is that, so you don't see that phase shift because now you fix your now we fix the reference sine and cosine functions to whatever the starting time, and you're not shifting them in the data window. And now you will see a stationary Phasor as you compute new values. As long as the signal remains constant, you will see the same value. So this is the idea of recursive, or you can call this the sliding Dft. In this case, we are computing only the fundamental components. And sometimes you may want to compute a second harmonic. You can do that, or even any other harmonic that you want. And typically, we are interested only in the fundamental. Okay. So all these calculations should be happening very nicely as long as your signal frequency remains at the nominal value, because now you compute the theta value, assuming your frequency is equal to nominal value, right? But once the frequency of the signal deviates, your estimations is going to be slightly, it will have some errors, right? So when you have a, let's say, sinusoidal, like a signal with the frequency, let's say, equal fundamental frequency equal to 50 Hertz or 60 Hertz. So if we use 50 Hertz or 60 Hertz Dft, then all the frequency components that you compute would be at fundamental plus its harmonic values. So we call this the frequency bins. But when the frequency is slightly changing and this situation changes because now you have two different frequencies because your reference sine and cosine functions are of the same period, not the same period of signal, then what would happen is something like this. So your estimated magnitude, you would see some ripple like this. And this ripple, you can show that, actually you can show mathematically that this ripple is has a frequency as twice the nominal frequency, right? Or close to nominal frequency, twice the nominal frequency. And the form of your signal, actually you can show that it would have two components. So one, let's say, one component of the magnitude is P times X, and its phase angle will be changing in this direction at the rate of the difference between the actual frequency and the nominal frequency in the anticlockwise direction. And there's another component rotating in the opposite direction at a frequency which is omega plus omega naught. So this, and so sum of these two is equal to the actual pressure that we observe. So Px would be something like that, and then the Qx would be something like that. So Qx is, Px is rotating in this direction in one frequency, and this one is rotating at a higher frequency. So basically, the sum of these two is the actual pressure that we are observing. So you can see the sum of these two changes because the this frequency and this frequency are different, right? So this is basically double the frequency. Therefore, you will see it as a, so this typically this part, the magnitude of this is small, and therefore the actual value plus some ripple you will see in the magnitude estimation. And of course, in the phase angle, now, because your frequency is different from nominal, your frequency, your phase angle will continuously change. But also, you will see that there's some ripple in the estimated value. So that is what happened when the frequency of the signal is deviating from the nominal frequency. So it is a good condition. So obviously, I know because this is giving some errors. So this phenomena is normally, like in the signal processing, you call it the spectral leakage. So this is happening because you assume the n samples contain exactly one cycle, but when the frequency changes, so it is not, and therefore you will see the discontinuity in the signal, and that discontinuity is what causing this spectral leakage. Remember, because we start with the Fourier series, and Fourier series is a continuous periodical signal. Now, when there's a discontinuity, so that's not following the assumptions, right? So this, as I mentioned that, so when you use the DFT with endpoints, you get n frequency points. And so these k values are called the frequency bucket numbers. So these are fundamental plus harmonics and so on, right? So you're typically, if it is exactly the same like your window contains one cycle. So all of your, and if it is a pure sinusoidal, all of your, you will only see this line, red line, and you will not see other lines. But if your frequency is slightly different, so now you would start to see like some other frequencies like this. So this is called the spectral leakage. And so how do you correct this problem? There are a number of ways to like minimize the impact of this. One solution is called like applying a windowing function to do that. What it does is when you take the like the signal window like this, so you have like this, so this part of the sample window contains this type of signal. So before you apply Dft, what you do is we multiply this with some sort of window function, and then so make the signal something like that. So because these far away ones are having a smaller magnitude, the impact of this spectral leakage would be reduced. So there are many different possibilities for windowing functions. So one is called like a Hanning window. So it is something like this. It has this type of phase. So you can use like a cosine function or Gaussian function, raised cosine. So there are different window functions which you can use. Now, one problem with this method is like when you use the windowing function, you need to use a longer window, because if you take one cycle and you can't apply this window function, because then the signal will get distorted. Right? So you need to contain at least one full cycle, and then other parts could be like tapered off. And of course, when you do that, you can see that now you're using a longer window, and that will introduce some latency into the computation. So the second method to avoid this problem, mostly used in protection relays and so on, is called the resampling. What it does is that, so when you do the Phas calculations, you can also calculate the frequency, right? So when the frequency deviates, you can know that it is deviated, and you can recalculate what should be the sampling interval if you want to contain n samples in one cycle. So, so in the digital domain, you can use some, let's say, let's say the yellow, like these points are the original samples, then you can, based on the frequency, you can recalculate where these samples should be based on the like actual frequency, and then you can either use interpolation or extrapolation technique to get the new sample values, usually interpolation samples. And now you can apply Dft based on the new samples computed, so that there are exactly n number of samples in the one cycle. So then you will not see this problem. So this is normally called the variable sampling rate. So this is often used in the protection relays, but when you do the synchro-based estimation, and typically this method is not used. The one problem, because when you are using the time tags and so on, so we need to report like a certain number of cases in 1 second, right? and their time tags then should be certain fixed values. So if we don't normally use this resampling or the variable sampling rate method when you're computing the synchro phases.
Excuse me, sir.
Yes.
We have only 3 minutes left according to the agenda.
Okay, so I think I have a couple of more slides, and we can stop at any point, okay, if the time is very strict. Okay.
No, time is not very strict, so we can continue until it's complete.
Yeah. So that is the basically the Dft base estimation, and you could see that it will work perfectly at nominal frequency, but then you will see some problems when the frequency deviates. Okay. So what are the other possible methods? So one is the use of least square estimation, right? That means you get like data window, so you have n data points. Then you try to fit a signal to these data points that you have. So basically, you can express your time domain function as time function of time plus some parameters. Right? So idea is to estimate these parameters. So if it is a sine signal, so these parameters could be your amplitude, your phase angle, and maybe the frequency and so on. Right? So you can formulate this as a minimization optimization problem. So you minimize the error between the actual signal and your fitted signal. And so if your function is a linear function, you can estimate your set of parameters. You can express this as a times p. So A is like a matrix with numbers if it is a linear function. And you can easily estimate if you know what is A and what are the function, like a signal, then you can compute P. So if you're, of course, then you have to assume what is your function. So it's you can assume this as A naught plus A H. So H can depend on like 1 to H. So these are the harmonics. So these are the coefficients of sine and cosine function. So if you're interested only the fundamental, you only have n equals 1 case. Then you have to estimate A0, AH, EH, and so on. So this is the DC component and so on. So with many different observations, you can write all your observations should be based on your signal model. You can construct your A matrix. And so it multiplied by these parameters, you give the your signal, and of course then plus some error. So this equation is satisfied. Like what we're trying to do is we have to minimize these errors. So we calculate these parameters so that this is minimized. So once you get these numbers, so your signal is defined. So if you know A1 and Bn, then you know the real and imaginary part of the phasor, right? So this, again, you can see it works fine. Like if you know if the signal is of the fundamental, like or the nominal frequency, right? As soon as your frequency is different, that means your omega is also a parameter that need to be estimated. Then this equation will become nonlinear equation, and then you can use the nonlinear least square estimation, or you can use a kind of iterative method to estimate the frequency. How you normally do is that you use your linear function and you compute, because to compute these things, you need the frequency too, right? So you can use the frequency that you estimated in the previous time step to compute this. And then you can compute your pacer, then you know the pace angle. So based on the pace angle, you can compute the frequency again. And with the new frequency, you can recompute this matrix and compute new set of parameters. You can iterate until you get the convergence so that you can estimate the new frequency and the new real imagery part. So that is the approach used in the least square estimation. And now you can see that it involves some iterative calculation. So if you're doing it in a really fast manner, so this is computationally a bit more involved. And of course, if you want more accurate estimation, you can actually represent your signal model that you use here as a dynamic pace. That means you assume these are also function of time and so on. You can use the so-called Taylor Fourier transform to represent the signal. So with this model, so you can actually estimate the magnitude, phase angle, frequency, and rate of change of frequency at once as a using the least square method, right? Of course, I'm not going into detail, but if you want, I can send a paper which this algorithm, you can also look for these things. So there are different methods as we discussed, like Dft method, and you can use wavelet-based transform to do that. This is the discrete Fourier transform. And optimization is basically, those are the least square methods. And also there are Taylor Fourier transform based methods. And there are some advantages and disadvantages. So I'm not going into detail because of the time. Typically, like a Dft works quite well because it is very easy to compute and it has a good harmonic rejection. The only problem is this spectral leakage at the out of like off nominal frequencies. Right now, so this, what we discuss is just the pace estimation, and to make it a synchro pacer, you need to basically synchronize your reference sine and cos function with the 1 pps signal from the atomic to the satellite clock. That means your cosine signal, reference cosine signal should start, or its zero pace angle should happen at the start of the new second, new UTC second, right? So this, if you have this signal, it is quite easy to do that. And of course, you had to resynchronize this one at the beginning of every second, because otherwise your clocks will drift with the time, right? So every second you try to synchronize with this 1 pps signal. Normally you don't hard synchronize your all the sampling point with the satellite clock, but your time stamping need to be properly done. Remember, I mentioned about two things like a P class and M class. And if you want to satisfy these measurements, you need to estimate the pacers and then apply some additional filter into your real and imaginary part to get. For example, the standard like gives some, like they call reference filter model, or one you can consider it as an example of a filter which you can use, but you can use a different type of filter. Only thing is that you need to satisfy the accuracy requirement. But the standard says that if you use this filter, you can achieve that required accuracy level. So for the P class, it's a very simple filter. Filter coefficients look like this, and it spread over two cycle window. And of course, at the off-nominal frequencies, remember that we mentioned that there is some oscillations and going on. So when you do this filtering, so there will be some error introduced. And so you multiply your estimate by certain correction factor, which depending on the frequency deviation. So, and to compute the frequency, actually you can, for example, we define the frequency as the difference between the rate of change of phase angle. But typically, like when you compute the frequency, so you use actually for most recent sample of the phase angles, so that you get some sort of average rate of change of the phase angle. You can use this formula. So this is given in the standard. For the M class, the filter is not directly given like that, but the filter frequency response should really, it's given this kind of diagram. So your filter frequency response should lie within this white area. So you can design your own filter to have this kind of response. But the standard also give one example of a filter, and the filter coefficient you can compute like this using a sinc function, and coefficient would look like that. And it basically spread over several cycles. So the filter order will depend on your reporting rate and the sampling rate. So this gives the number of filter coefficients, how it changes the samples per cycle and your reporting rate. So it's a bit more complicated to implement the M-class filter, and you also need a lot of memory if you're using a high sampling rate and a high reporting rate. I think maybe that's all I wanted to say today. And maybe if you have any more questions, I can try to answer as best I can do. Okay. Yeah, thank you for listening for this long talk. Okay.
So thank you, Professor. Your insights have been absolutely wonderful, and I'd like to thank you all for being a brilliant audience, and I hope you got something new. Professor Rajapakse, we are so grateful for your time, knowledge, and expertise you shared with us today. So once again, thank you very much, and please accept this digital token of appreciation.
Okay.
So at last, Professor, we are truly grateful to have you today, and especially for sparing your valuable time.